Welcome to this video on energy and power in an electrical circuit. Over here I have four resistors connected in series with one another and connected in series with a battery over here. Now remember that in series, if you haven't watched the capacitor videos from before, in series means that between any two circuit elements there's no split junction or node that gives the current a path change between the two circuit elements. So in other words, there's only a direct path between any of these circuit elements and actually between all of these circuit elements. Now we're looking at this from the perspective of energy. Now recall that the battery over here, let's call this battery B1, the battery is going to provide X amount of energy to the circuit. And we want to know how much energy is needed in order to heat up these four resistors to some desired temperature. Now we don't really care about the temperature, that's not really the point of the video, but what we do care about is looking at how much energy these particular resistors use up, so to speak, in order to heat up. So if we think of energy transfer here, any heat that's going to come off of these resistors is going to have to come from somewhere. It can't just spontaneously come up on its own. So if we think about each of these as giving off a certain amount of heat, all the heat added up together of these is going to be equal to the amount of energy that the battery provides through its chemical bonds. Now, a few things that we're taking into consideration here is that the resistance of the wires we're going to say is equal to 0. And we talked about that in the last video. We're also going to say that the battery itself, B1, so the resistance of B1 is also going to be equal to 0 ohms. Now batteries do tend to have a little bit of internal resistance, but we'll just ignore that to simplify the situation. So let's take a look at it. Now, I'm going to be looking at non-conventional current in this video, so let's go ahead and write that down. This is going to be non-conventional current. Now, when I say non-conventional current, what I mean is I'm going to be tracking the path of an electron rather than the archaic idea that little positive charges were being pushed, so to speak, through the circuit. So I'm going to say that electrons will move from the negative terminal of the battery through the circuit to the positive terminal of the battery. So conventional current would say it goes the opposite way from positive to negative, but I'm dealing with electrons here, so they're going from negative to positive. Now the reason that I want to do that is I want to look at how much energy is dissipated or how much heat is released by each of these resistors. So let's just track one electron. Remember that the kinetic energy of that electron is going to be converted, let's say, into the heat that's released over here. So the work that is done by the resistor on an electron with charge equal to Q, so let's write that over here, the Q is equal to the charge on an electron, we're going to say that that's equal to E times delta V. So the potential difference across the resistor, right, will matter to how much work is done on that electron as it passes through, in this case, R4. The same expression would be true for each of these resistors subsequently. So what I could say is the work being done on 4 plus the work being done on 3 plus the work being done by 2 plus the work being done by 1, all of those would add up to the total work that is being done on this little electron. Let's call him Bobby. So as Bobby moves through the circuit, the amount of energy that Bobby loses as he passes through each of these obstacles on his path back to the battery will add up to this amount. Now, if we think of the idea of conservation of energy, we know that the total amount of energy has to come from somewhere. Otherwise, where would Bobby have got the energy in the first place? Well, that's coming from the battery. Remember, the job of the battery, the work that the battery does, is the amount of energy provided to the circuit. And so the amount of energy that's provided to bobbies, so to speak, in the battery is going to be equal to the total work throughout the rest of the circuit. So that's going to be equal to E times delta V across the battery. So we know that the delta V across the battery is the greatest delta V, and we've shown before that things that are connected in series with one another, the potential difference between the 2 points on either end of the battery is the same whether you look at it from the perspective across this part of the circuit or if you look at it from the perspective of this part of the circuit. So this potential difference here is equal to the potential differences across each of the resistors. So when I set this up in a full expression, if I write that the work total done by the battery is equal to the work done across each of, or over each of, the 4 resistors. So if I write it in this way, just looking at it from the perspective of this one particular electron, I would write something that looks like this, which is a little bit redundant, but we're trying to put a point across here. Sorry, this is delta V4. All right, so we can see here that if we're just looking at this one particular electron throughout the process, that electron's value can factor out, and we can just look at the total potential needed to provide the potential across each of these particular resistors. Now this concept shows that the amount of energy that's being dissipated or used up by this particular resistor or this particular resistor, in other words, the amount of energy that's needed to supply all 4 of these resistors will be equal to the amount of energy that is given by the battery. If we want to look at it from the perspective of power, which is the rate at which the energy is dissipated or used up, what we need to do is look at the amount of work done in a given amount of time. Now, time brings in the element of current. And so over here, we haven't yet included the idea about current, but we do know that from our previous videos that delta V is equal to the current running through the particular resistor times the resistance of that particular resistor. Remember that this is only true if R is constant. So if I take this expression now and I put it in, substitute it in for each of these delta V values over here, I would see that the current total times the equivalent resistance is equal to the same product across each of these, but with a different value for each of the resistances. So we have something that looks kind of like this. Now we've established the fact that there aren't any junctions or breaks in this wire path, so the current at any point throughout any spot here would have to be exactly the same through any pathway. Now we can see here that we've included some sort of element in here that might be useful looking at the power because it includes something about time. So if we look at this idea here for power, we might write it something like this. We could say the amount of charge of the electron times delta V over T, and we see here charge over time, that's current, times delta V. So I times delta V is one expression for the power dissipated by a particular spot or resistor in the circuit. So we have to be very careful. It's not the same as delta V, but it is close. So we would write the power at any one of these particular resistors, let's use R1 as an example, is I times the potential difference across that resistor. Again here, I could take this particular expression, I times R, and substitute it in for delta V. So I maybe want to write it like this. We did number 1, and so this would be P1 is equal to I squared times R. So there are a few different expressions that you can use to show the amount of power that's dissipated by a particular resistor. The main idea here is to remember that energy, no matter what form it's in, is conserved. So the amount of energy provided by the battery is the same as the amount of energy needed to heat up or to move an electron across any of the resistors. In our next video, we're going to take a look at what is known as Kirchhoff's rules, and those are basically the same thing that we've set up right now, but what they're going to enable us to do is be able to calculate different points in the circuit, in other words, the resistance or the current at any given point in a circuit. And we'll look at this for both series configurations and parallel connected configurations.